The topic of this presentation is machine learning for reaction wheel fault detection using simulated telemetry data. This work was a collaboration between the University of Colorado Boulder, which I'm affiliated with, and Veris Research. Fault detection is very important for mission success. It's not a matter of if a fault is going to happen, but when it is going to happen. And the current approach uses ground operators to comb through large amounts of telemetry data. This is expensive and hard to scale, especially when you consider constellations of tens of thousands of satellites. Also, the effects of faults on data can be quite small, and ground operators might find it difficult to detect anomalies. The use of machine learning aims to improve on these drawbacks. ML tools are easily scalable and can be fed large amounts of data. And another point to consider is when we use synthetic telemetry data, we know exactly when the fault happened and what type of fault it is. So we can easily benchmark these algorithms. For the problem statement, the scenario is quite simple. It was inspired by the VPM satellite with the goal to do science on Earth. Two attitude modes are simulated, a sun pointing for charging up the batteries and an Earth pointing for generic sensor measurements. These attitude modes change every 5 hours, as you can see in the bottom left image. Two types of faults were simulated, both regarding the reaction wheel subsystem. The first is a reaction wheel friction increase of 5 to 20-fold, and the second is an error on the reaction wheel speed measurement, which now outputs a constant value instead of the true reaction wheel speed. We also dispersed the inertia matrix values to see how the algorithms perform against overfitting. We were worried that slight changes in tracking performance would make the algorithms think that that behavior was anomalous when in fact it wasn't. For all these simulations, we use Basilisk, our in-house modular open source and flight-proven physics and flight software framework. And for this particular work, two new modules were added: a thermal module that simulates the temperature of the reaction wheel speeds, and a wheel speed encoder, where we inject the encoder faults. The output of this module is then fed into the GNC loop, as you can see on the bottom left diagram. As for the machine learning algorithms, our first approach was to use unsupervised learning algorithms. We applied Gaussian mixture models, one-class support vector machines, and long short-term memory neural networks. However, we saw that these algorithms didn't perform quite as we'd expect on the encoder faults. And so as a second approach, we used supervised learning algorithms. These supervised learning algorithms are neural networks, which we call single row classifiers. And they take the state variables as an input and output the probability of a fault having occurred. We also applied the transition detection algorithm, which is very similar to a single row classifier, but we also introduce the difference in the current state and points in time before and after the current time step that we're working with. We also applied the no change detection algorithm, which looks at variables that have been frozen in time for quite some time, and this is particularly useful for the encoder faults. As for the numerical results, I wanted to start with just a generic figure analysis because I'm going to present very similar figures and it's important to understand what's going on. The cyan lines represent the attitude mode changes, and these are quite important in our analysis because we found that the algorithms we used consistently flagged attitude mode changes as anomalous. The way we tackled this was to disregard some data immediately after an attitude mode change, and that seemed to fix the problem of too many false positives around the time of an attitude mode change. The shaded red regions correspond to the period where a fault has already occurred, and the stars represent the algorithm detecting an anomaly. The y-axis represents how confident the algorithm is that a fault has occurred, and obviously the higher it is, the more confident the algorithm is that the fault has occurred. We also introduced which variable was used for testing and training. So one of the main takeaways from this work is that it is very important to know how to use the variables from the telemetry data. For example, looking at the top row, we see that there are a lot of false positives when we use only a single variable for testing and training. The way we tackle this is to combine multiple variables of the same subsystem into one, and that seems to decrease the probability of us getting false positives, especially when we use the temperature variables. Another important takeaway is that some variables are more useful for fault detection than others. And we can see here that, for example, the temperature, the algorithm detects the fault almost immediately. Whereas when we look at the attitude, we see a lot of false positives. Actually, these false positives relate to when the attitude goes over 180 degrees and we switch to the short rotation. For a comparison of the unsupervised learning algorithms, we see that they fare pretty similarly, although we note that the LSTM still has some false positives, whereas the GMM and SVM algorithms don't. We notice that the GMM and SVM algorithms are particularly suited to detect out-of-range anomalies, whereas the LSTM was very good at detecting breaking the pattern anomalies. And this makes sense because LSTM is very useful in analyzing temporal behavior. So this table summarizes the results for the supervised learning algorithms. Each entry has two values. The first value is the probability of detection, and we want that value to be as close to 1 as possible. The second value is the probability of false alarm, and we want that value to be as close to 0 because we don't want a lot of false positives in our supervised learning algorithms. So looking at the single row classification and the transition detection, they fare pretty similarly and they do quite well. We have high probabilities of detection and low probabilities of false alarms, which is exactly what we want. However, when we look at the no change detection, we see that it's only really useful when we talk about encoder faults. For friction faults, this approach doesn't really work, but for encoder faults, it detects every single anomaly without giving any single false alarm, which is exactly what we want. If we look at the right side of the table, we have the results for the inertia uncertainty tests. And again, we see that the single row classification and transition detection fare quite well. The probability of detection is close to 1 for most of the time, and the probability of false alarm is close to 0. We do note that when we train for longer, so when we train for 40 days instead of the usual 1, 2, the probability of detection goes up a little, and the probability of false alarm decreases too, which is to be expected. If we train the algorithms for longer or with more data, then we expect them to perform better. So to conclude, some variables are more sensitive than others. The temperature and power are particularly useful, whereas something like the attitude components aren't really useful in fault detection. Also, combining multiple variables into a subsystem and analyzing that overall anomaly confidence yields much better results because it removes some of the false positives that we were getting. We also saw that the algorithms are robust to inertia matrix dispersion, and this is particularly important because the digital twin is never going to be exactly the same as the real spacecraft, and so it is important that these algorithms work well with slight deviations. We also saw that the absolute mode changes were a great source of false positives, but by only removing about 1 to 2% of the data, we were able to remove this problem in its entirety. So all in all, machine learning algorithms were successful in detecting the reaction wheel faults. And I think this is a promising field of research with the potential to change the way we approach post-launch mission operations.